streaks of color arcing across a rain-filled sky. For thousands of years, we've tried to decipher these magical displays. But so many answers remained beyond our reach.
I can't touch the rainbow, but it feels like you can reach out and touch it because it's right here.
And today, from inside a precision engineering lab to the business end of a firefighter's hose, scientists and enthusiasts alike are breaking the rainbow's code, generating images that even Isaac Newton thought were impossible.
This is the 9th rainbow order. Oh, that's cool.
Revealing new tools that may one day help discover habitable planets beyond our solar system.
That could tell us if the planet itself is suitable for life as we know it.
They can appear in the most unlikely places, in a captivating assortment of shapes and colors. But make no mistake about it, anytime you catch a glimpse of a rainbow, you're witnessing a scientific marvel in action. And it all begins in the very drops of liquid where they're born.
Well, this is our model of a raindrop. It's a glass sphere about 3 inches in diameter.
Dr. Raymond Lee from the U.S. Naval Academy is one of the world's leading thinkers on rainbows. And that research has led him deep into the center of the raindrop. Here, like a prism, the clear drops of water break the sun's white light into a colorful array, which in turn reflects off the back of the raindrop, then refracts or bends on its way back out.
So what we see in that single droplet is going on identically in thousands or even millions of individual drops in a rain shower.
To get a closer look at the mechanics of the rainbow, Dr. Lee makes a visit to Captain Joey Ortenzo at the local volunteer fire department. The laws of physics tell us that anytime you have bright sunlight and water droplets in the sky, you have a chance at a rainbow. And your chances are best with a mist rather than a hard rain.
And our first rainbow of the day, I can see here.
And to get your best view of a rainbow, you need more than just ideal rain conditions. You need to make sure you're standing in the right place, with the sun directly behind you. From this, and only this vantage point, you can witness the sun's rays return to you as a rainbow, 40 to 42 degrees from their original direction. This mathematical relationship holds for water anywhere in the universe. Every rainbow is unique, but all follow the same strict laws of nature. A fact that might frustrate those trying to discover what lies beyond.
So you can see online all kinds of videos about people claiming to go through the rainbow, but it's all a mistake of perception.
Dr. Lee and volunteer Max Ondrusik are preparing a demonstration to see what actually happens when someone tries to go under his own rainbow. Max gears up with his firefighting suit
Rolling,
and a pair of waterproof cameras.
rolling. All right, shoot it up. Let's take a walk toward the rainbow. Well, you're all wet, so you got through the spray.
Yeah.
What happened?
So as you're going through, it gets a little bit brighter and mist starts getting in your face. But basically the rainbow enlarged a little bit as you got closer and then just got real bright. And then as you started getting towards the end, just slowly disappeared.
It went away.
Yep.
You have a compelling visual sensation that you're walking through the bow, but in fact, all that's happening is you're getting beyond the source of the water droplets, and that shuts it off. But the end result's the same. Your rainbow and my rainbow are different, and they look the same when we're standing right here next to each other.
In fact, every individual sees their own rainbow. Even your individual eyes see their own rainbow.
And the reason is, the rainbow isn't an object out there in the landscape. It's just an image of the sun.
When that image of the sun is reflected twice inside each raindrop, we see double rainbows in the sky. And for centuries, scientists have been on the lookout for evidence of an elusive third rainbow order.
Yeah, so the third order rainbow is in the wrong spot to be easily visible. You actually have to look right back toward the sun. And because of that, it's very difficult to ever see by eye.
And in fact, people such as Newton speculated that they probably were inherently invisible.
But now, in the age of digital photography, skywatchers from around the world have been working to prove Newton wrong. Enter Michael Grossman, an engineer and rainbow hunter, who achieved his moment in the sun one rainy spring day in Kampfelbach, Germany.
And I saw on the left side a big brightness and colorful rainbow from the first order, the primary rainbow. And also the secondary rainbow was visible in the sky, and I think, wow, that's very amazing. So it's maybe the best chance to see the rainbow of the third order.
And with the sun now peeking through the rain, he turns his back on the double rainbow.
So I go 1-2 steps and I stand in the shadow from the tree to shield the sun. It's very important to shield the sun. And then I make a finger trick. I spread my fingers 2 times so we have the right angle for the rainbow of the third order. I took my camera and first I saw a small shimmering. I'm not sure, but I think it was very slightly shimmering. So I put the camera on and take 1-2 shots, and the rain stops. After 2 minutes, rain was over.
He wouldn't be the first to witness a third order rainbow, but would he be the first to capture the evidence?
For many hundreds of years, we had only a few sporadic reports from scientifically knowledgeable observers about seeing such rainbows in the wild, and in fact, this is something that has been seen, never photographed.
By fine-tuning the light levels of his image, Grossman reveals what appears to be the faint color bands of a third-order rainbow. He then sends the image off to a pair of colleagues for confirmation.
And 2 days later come the response, Michael, you did it. And that was so happy for me to catch the rainbow third order first time ever.
So we have a centuries-old invisibility lifted. The veil was up, and we can now see these never-before-seen, very rare phenomena were there for the world to admire.
Grossman had captured a phenomenon that even the greatest minds in physics had missed. And Grossman's work isn't done yet. He wants to observe even more rainbow orders. Putting his engineering skills to work, he's created a device that will generate rainbows beyond what can be observed in nature with our own eyes. He calls it the Spectrodrome.
The Spectrodrome is a little laboratory to create rainbow lines on a screen. So we have here the metal ring with a diameter around 30 centimeters. Inside here, this is the screen. There are 2 holes. Here is a little hole for the incoming light, and here is a bigger hole for the exiting light. So then we have here a special water container with a pump inside.
Grossman has modified a common slide projector so that it generates a focused beam of white light. He'll carefully aim that light through a column of water pumped from an attached reservoir.
And with a sheet of paper, I calibrate the light beam nearby the water jet, so we have a very sharp light point in this position.
For the spectrodrome to work best, he'll need to keep that water jet free of bubbles or vibrations, and he'll need to kill the lights.
So now it's fine. We have turned off the light, and now we can clearly see the first 4 rainbow orders. This is the first order rainbow, and this is the secondary order rainbow. On the other side we see the third, and this is the 4th order rainbow.
As in nature, these rainbow segments are created by light reflecting and refracting inside individual drops of water. And with a stronger light source, Grossman can generate even more reflections, well beyond what has ever been captured by human eyes.
Now I hit with a laser beam the water jet, and I can slide to the right and to the left, and when we do this we can see a lot of rainbow orders.
Because laser light is monochromatic, these rainbows are completely green. And even though he's using a simple consumer-grade laser, it's still powerful enough to damage eyes or camera equipment. Both he and the film crew need to be extremely careful.
Here you can see very faint the laser beam who hits the water jet at the outer edge and produce all the internal reflection and all the possible rainbow orders. And we see here the first rainbow order. Here is the secondary rainbow order. Then the third internal reflection shows us the third rainbow order here. On the other side, the 4th rainbow order here. And here the 5th. Oh, it's going up to the 6th. The next internal reflection shows us very clearly the 7th rainbow order. Whoa, that's very cool. Very clearly. And on the other direction, this is the 9th rainbow order, very faint. Whoa, that's cool. And also in this direction, but you cannot see clearly. Maybe at this direction there must be the 8th rainbow order.
With his spectrodrome giving him a virtual 360-degree rainbow map, Grossman can now go outside and reveal where to find these hidden rainbows on the next rainy day.
So at the point of view at this field we have the first rainbow order, it's called the primary rainbow, and a little bit outside there is the secondary rainbow. When we take a look to sun direction, we have the 3rd rainbow order and also nearby the 4th rainbow order. When we take a look back to the anti-solar point, we saw inside the secondary rainbow we have also the 5th order rainbow, but only the greenish part of it. And inside the primary rainbow we have the 6th rainbow order, but it's not possible to see it because it's too bright inside the primary rainbow. Go back to the sun direction. It's funny, I know. We have the 7th rainbow order, and around 20 degrees we have the 8th rainbow order, but it's not possible to see it because it's too bright. At an angle of 90 degrees from the sun we see the 9th rainbow order. Very faint, and I think with contrast enhanced maybe it's possible to see it. Actually, the sky is full of rainbows when we have a lot of raindrops and sunlight is shining.
And it's not only our earthly sky that brims with rainbows.
We think of the rainbow as an earthly phenomenon, but in fact, a rainbow can exist on any planet where light hits liquid water or even potentially any kind of liquid.
For example, you can see them in methane droplets on Titan.
Scientists believe that when sunlight pierces Titan's thick, orange-hued atmosphere, it can create massive methane rainbows, taller than any found here on Earth. And now, planet hunters on the other side of the globe have picked up this search for deep space rainbows. Why? Because they just might give us the best evidence of liquid water and the potential for life on other worlds. At the Australian Astronomical Observatory, technicians are preparing their 4-meter telescope for a journey into solar systems beyond our own. Lucina Katsiora-Hudchar and Jeremy Bailey from the University of New South Wales begin work on installing a remote sensing tool called a polarimeter onto the bottom of the telescope.
The ones on your side need charging?
Yes.
Okay. So what's happening here, we will have the light coming down from the telescope to the hole in the instrument, into the aperture of the instrument.
Their device, which they've named HIPPY, the high-precision polarimetric instrument, dissects light traveling from distant stars.
Oops, there we go.
It's one of the most light-sensitive instruments on the planet. Even the tiniest amount of light pollution could distort their work.
All right, that's in. So we make sure that if there is any light even on flickering on these devices here, we just cover it with tape. And this is important for keeping the precision of our measurements.
Okay, let's do it.
Okay, all done.
HIPPY will analyze cosmic starlight, looking specifically for traces of polarized light, a key connection to the science of rainbows. Starlight travels through space in a chaotic array of light waves. But the waves that collide with a clear liquid, like raindrops, in a planet's atmosphere, reflect back into space in an orderly, polarized pattern. We can't separate out this polarized light with our naked eyes, but the filters inside HIPPY can. And a key technology that allows it to do so works much like a pair of sunglasses.
If I have these polarized sunglasses on, they are transmitting light that has a particular orientation of electric field. And if I rotate my head with those glasses on, then I can change the orientation. If you do that while looking at a rainbow, you will find that the rainbow is very highly polarized, and you can actually, if you wish, make at least a piece of the rainbow go away by orienting the polarizer at just the right angle.
Joe Shaw from Montana State University demonstrates this effect with a sheet of polarizing filter and a rainbow generator he created with a few simple supply store materials.
The top looks great and the side goes away. Now the top goes away and the side is nice and visible.
Inside HIPPY, a process similar to this analyzes the polarity of light passing through the telescope hundreds of thousands of times per second. When HIPPY's internal filters detect traces of polarized light emanating from the atmosphere of a distant planet, they'll begin tracking its orbit around its home star. And if the flow of polarized light peaks at the moment when the distant star, the planet, and HIPPY are positioned in the so-called rainbow angle, they'll have strong evidence that they've found water.
So now that we installed the instrument, the observing will take place from this control room.
For Lucina and Jeremy, their window into deep space comes across as a strange code of numbers and symbols.
These squiggly lines actually show that there is a polarized signal coming from the object on which we actually pointing a telescope. In the end, I hope that we will be able to say some more about the atmosphere of the planet we're looking at, whether it has potentially rainbows, so droplets of waters in the atmosphere. That could ultimately tell us if the planet itself is suitable for habitation or it's actually habitable for life as we know it.
Just like on Earth, an alien rainstorm on a distant planet, hit with a burst of starlight, would create a vibrant rainbow display of polarized light. A signal from across the cosmos, perhaps, that life is possible beyond our Earth. An invitation to venture out and explore.
Rainbows are important to us not only as lovers of beauty in the natural world, but also as intellectually curious citizens. They show us how optics works in nature with a splendid display that has all kinds of rules and constraints that come from optics and physics. The rainbow should be an object not only of aesthetic delight, but also of intellectual curiosity and satisfaction of that curiosity.